Today's astrobiology seminar. We're going to have a couple of astrobiology student rotation talks today. We're going to hear from Hector Delgado Diaz and Gio Canan a little later today. First up is Hector. So if you're not familiar with this, what we're doing today, so astrobiology graduate students go and take a quarter where they perform research outside of their dissertation. And then they have to come back and report to us and let us all in on all the great stuff they learned for they were away for a quarter. So this is the last step of that rotation process. So as I said, first up is going to be Hector, who's going to tell us about his research from this past summer. And so it'll be about 25 minutes. We'll have time for questions, and then we'll switch over to Gio. So with that, I'm going to turn it over to you, Hector.
All right, thank you. All right, good afternoon, everybody. My name is Hector Delgado Diaz. I'm an astronomy graduate student in astronomy. I said in astronomy, and I'm gonna be talking about my summer rotation in Universidad Nacional Autónoma de Mexico. And I work with Dr. Antigona Segura, and we also had a team, others such as Arturo Miranda Rosete, Guillem Gronov, Ira Payton, Vladimir, and James Gaston. So we all kind of like work on this project asynchronous. So I'm gonna be explaining you why we want to study the effect of high energy particles from a stellar flare in the atmosphere of potentially habitable exoplanets around dwarf stars. So like, why do we want to study exoplanets around dwarf stars? Well, I'm just gonna make a case for you to be convinced. And one of the things is that there's many M stars around our Milky Way. There's about 70 to 80% in the Milky Way, and in our solar neighborhood, there's a lot of them. So there's a big abundance of them. Not only that, because they're also lower luminosity, they're smaller, and because of that small radius and the lower luminosity, when a planet is in between the line of sight of us and the star, we can see that the brightness of the star diminishes, so therefore making a detection of the exoplanet. If you were to compare the same exoplanet around another star, with, let's say, like a sun, which is bigger, then that ratio of the shade of the star on the planet on the star is going to be way less, and it's going to be really difficult for us to detect and study that exoplanet. Also, the atmosphere of the exoplanet can also create effects on the light that we receive from the star when observing that transit. So with a high abundance and a small radius, I think that the M stars are good candidates for us to look for exoplanets and maybe search for life in them, since they're like very, very present around us. We can just study them easier than other stars, and this could maybe be, numerically speaking, a place where we could probably find signatures of life due to the high number of stars around us. Now, the thing is that M stars can also pose threat for life. And here I'm showing you, this is a work done by France in 2020, where the red color shows, perfect, it works. It shows quiet 699, so that's a star GJ 699, it's an M star. It means quiet, meaning that the solar activity is way lower. It's like the lowest or the minimum in its solar activity. And we compare it to the quiet sun, which is also its lower solar activity. And we can see that on the extreme ultraviolet, our M star has a higher flux compared to the sun, making it then that the XUVs, which is the X-rays, and the UV are stronger than the sun. And when they're stronger, this could lead to a loss in the atmosphere, such as thermal or ion escape, but it could also mean photolysis of the molecules in the atmosphere. For example, one of our important molecules that I'm gonna be talking about is ozone. And we can see that this ozone is affected by ultraviolet light. So we want to study how that higher activity of UV affect the molecules in the atmosphere, which are important for life. Another thing that it's important on M stars is that their structure, of the insert structure, we can see that, for example, this would be like a star greater than 1.5 solar masses. So most of the radiation, most of the heating transfer that happens in the outer envelope of the star, it's by radiation. Whereas for a star like the M, it is fully convective, and those cycles of convection are the ones that create magnetic fields around the star, creating a lot of what we call stellar flares. And in here, you can see, for example, you can see that when a stellar flare happens, that's a burst of light in the whole electromagnetic spectrum. But not only there's also a burst of light, you can see that particles fly out from the star, and those particles can reach the planet that is orbiting the star. So here, for example, this is just a simulation. It is sped up. Sorry for the. This is just showing here something. This is what they call the Carrington event that happened in the 1800s, where the sun bursted out with a solar proton event. There was a bunch of protons from solar activity from the sun that reached the Earth. And if we look at those particles arriving to the Earth, we can see that it meshes those lines here. That's the magnetic field of the Earth. You can see how those lines can like disrupt the magnetic field and reach, well, potentially reach the atmosphere and strip away molecules from the atmosphere. Thus, could be affecting potential for life or life if it already existed. In here, this is just one of the stellar flares observed in 1991. This is like the earliest recorded flare that we have observed in the optical and the ultraviolet. And in here, I'm just showing you that for the ultraviolet and the optical, this is like on the top, this is the flux when the flare happened. And on the bottom, this is the flux when the star is quiescent. And we can see that when the flare happens, there are peaks. For example, the hydrogen line are increasing in flux. So the flare, so when a flare happens, it is increasing the flux of the star at different UV and optical. And just in case, something to know is that when they observe this flare in the optical, so they were able to observe the flare the whole time in the optical, but in the UV, they unfortunately didn't have consistent data. So they had like sparse data about the UV observation. So they don't have a continuum of that UV. So what some scientists did in 2010, so Antigona Segura, which is the doctor that I work with in this research rotation, what she did, the team did, they kind of like stitch those UV observation with the optical, and they were able to create a continuum of fluxes of the flare, and they divided that flare, the whole time sequence of the flare, into time steps. So what you see here on the left side, I know it's a little bit busy here, but on the left side, this is just the quiescent flux of the star. And then we see here, each line represents a time step of the flux, how it increased in the impulsive phase of the flare, when the flare was like increasing. So it gets all the way to like 1497 seconds. And then after that, they did a stitching of the flux, how it gradually went down. So they were able to have that flux continuum for the whole time the flare happened. And they took that flux, and then they used a photochemical model to understand how is the atmosphere affected by those flares. And what they look here on this right side, we can see on the y-axis, this is showing the fractional change of ozone in the column depth, meaning that the lower the number, that's the ozone is being destroyed in the atmosphere. And each data point represents one of those lines. So it's like a different flux of that line. And you can see how when the flare happens, the ozone column goes down. However, it goes down by about 1%, which is not much. And then after a couple of years, it just stabilizes. Not even a couple of years, a year, it just stabilizes. And we get back the ozone flux, ozone column depth that we had before. But then they added the Carrington event. So they took the Carrington event from the sun, and what's the word? They converted it to like what would have been a Carrington event in an M dwarf star, because the sun is on an M dwarf, just in case. And when they like did that conversion, they saw that the ozone this time, it was lost by about 94%. And it took about 50 years for the ozone to recoup and get back to the same level of the column depth that was observed before the flux. So what we can see is that the flare itself, just the flux of it, does affect a little bit of the ozone, but the particles, the solar proton flux or the stellar energetic particles, which is not only solar proton fluxes, affect the column that does a 94% of a drop and then a 50-year to recoup can really mean a lot for life in the way that now the UV lights are reaching the surface of the planet. Another, oh, I forgot to do the credit. So this is Nakamura. Nakamura. So what they did, they studied Mars and the effect of the stellar energetic particles or SEPs on Mars and how does it affect ozone. So what they observed, it's that this is just a profile, an altitude profile, and then the density on the x-axis for each molecules. And what they observe is that the ozone, which is this line in green, has an anti-correlation of the HOx and NOx, or the HOx and NOx, odd nitrogen, odd hydrogen, however you want to call it. So when the ozone goes down, the HOx and NOx goes up. But then they studied that on the right side here, they took out the nitrogen, and they saw that there's a anti-correlation directly intertwined with the HOx molecules. So that means that the main culprit for ozone depletion has to do with the ozone. Now the pathway that they kind of signal in their paper is that, so we have this equation here, which is an HO2, and ozone is the one being HO2 destroys ozone and converts it to oxygen and OH. However, they say that this is not the equation that destroys ozone. What they think is that this equation here, so hello, there you go. Okay, so this equation here, it's the one being it's the one that they see that it has a higher rate of production of oxygen, and then that oxygen and the OH, for example, it mixes with carbon monoxide and creates CO2 and atomic hydrogen. Those two, the hydrogen and the molecular oxygen, they both go back to this equation and then create HO2, and then that HO2 keeps in what I'm saying here is that the HO2 keeps destroying the atomic oxygen. And when the atomic oxygen is destroyed, this equation on the bottom decreases because we don't have that reaction affect that reaction for producing ozone. So the one that is affecting ozone, it's the HOx molecules and the loss of atomic oxygen. Now, in 2018, Herbst recalculated what would have been a Carrington event for an M-star, and they use different new data from the GOES satellite. And when they calculated the new solar proton flux, for example, the star that we looked at, I forgot to mention that. So the star that we looked at FLARE was AD Leo, and Segura et al. They use this estimated proton flux of 10 to the 8 for their calculations. But then Herbst, in their work, they show that 10 to the 7 was the best case for the solar proton flux. So that means that there's a order of magnitude less than the one Segura used. And because these proton fluxes, the stellar energetic particles, they are geometry dependent. So the only way for a planet to be affected by the particles is that the particles have to reach the planet. So when Segura calculated this, they did an upper limit because they threw all the particles to the planet. So that means that the upper limit needs to be recalculated. Oops. Needs to be recalculated since we have an order of magnitude less. And that's where I come into play. So my objective of the research rotation was to calculate the total production and destruction rates of the atmospheric molecules when a stellar energetic particle event happens. So how does that affect the destruction and production rates for different molecules in the atmosphere? And then I had to create a code that adds the rates from the SEPs event to a photochemical model that includes a flare event. So I'm adding the flare plus the particle event that destroys the molecules in the atmosphere or produces them. And then I will analyze and calculate the fractional column change for ozone and molecular oxygen, as we saw that Segura did in their paper. Some things to note is that I use an Earth-like planet. The star that we use is an AD Leo, and the planet is in the habitable zone of the star. This is at 0.16 astronomical units. And then I use two different templates. I use Earth-like with 60% CO2 and a high hydrogen molecule, and an Earth-like 60% CO2 with a low hydrogen molecule. Arbitrary, I just use those. And then I just added one flare, and with that flare, just one event of SCP happening. And I say that because in M stars, it is more, like I said, it is a convective envelope. We expect flares to happen more frequent. So this is just like, this is just the basis of the work. We're just adding one flare, see what happens. And then future work would be to add more flares to see how that affects the atmosphere. For the first part that I had to calculate the production rates and destruction rates. So that was easy. Guillaume Grenov, he just sent me the data. He just sent me like all these molecules, a lot of them, destruction and production rates for different excitation states of each molecules. And between Antigona and I, we just decided which ones are very much intertwined with the photochemical model that we're using, and which are the ones that the photochemical model is not gonna be able to recognize. So we had to do a lot of like addition and subtraction and looking at which ones are related to what we want. Now, for the photochemical model, I use the one called ATMOS. So, oh, where's the sound? Oh, I had sound. No. Oh no, that's awkward. If I can make the sound, that would be amazing. Wait. Anyways, I'm hoping the people on the Zoom can hear it. I don't know. Anyway, so there was sound. It got ruined. So I use Atmos. Atmos is a 1979 code developed by James Casting. It was written in Fortran. It has two one-dimensional atmospheric models. One of them is the climate model, which calculates the temperature profile of the atmosphere. The other one, and it's called climate. The other one is photo. Oh, good. So photo is the one on the bottom. As you can see, it's a photochemical model that calculates the profiles of chemical species, including gaseous and aerosol phases. That's the one I focus the most, the photochemical model. And this one, what it does is it uses like a Mueller inverse method to calculate the flux and the continuity equations for each layer in this one-dimensional atmosphere. So it's just calculating how the fluxes vary through for each species in each layer. And then it creates like it just looks for the stability of each species for each layer. But then this only has the photochemical model. So we added, there's no sound, I'm sorry. This is gonna be awkward, but like, so we added FLAREMOS. So FLAREMOS is developed by Arturo Miranda. It's in prep. So it's just an updated version of ATMOS. It is literally the same. And it just contains the addition of one flare with 72 steps of time varying flux. So the 72 steps that Segura calculated that I show on the right corner that it was busy. So those steps are added into ATMOS and to see how that affects the photochemical model. And then, no sound, but I created Monstro SCP plug, FLAREMOS, that's how I call it. You'll see why I call it Monstro. So the SCP FLAREMOS, what it does, this is my contribution. So it's just an updated version of FLAREMOS that contains now the SCP event from Granov data, and just to see how that affects the atmosphere with the newly calculated SCP production and destruction rates from HERPS 2019. Unfortunately, if my idea, there was like a reference to a movie, I was referencing this movie. I like it a lot. So, but then that would have made sense, but now it doesn't make sense without the sound. Anyways, I wanted people to understand it. Oh no, now it's loading. Wait, there we go. Okay. So, oh, well, it's loading. Okay. There we go. Okay. So in here, these are the results. What I'm showing here is a 60% CO2 with a high hydrogen. And what I'm showing is on the y-axis is the same thing. This is for oxygen, the fractional change of oxygen. And instead of us seeing oxygen being destroyed, what we're seeing is a 5 times the oxygen levels before the flare being created. This black line, the straight line is all the SCPs added. So all the production and destruction rates, while the dotted line here, which is hard to see, and it's because it's on 0, it's no SCP added. So we can see that when we added the SCP, the oxygen changes drastically with all these production and destruction rates. Now, in here, hard to see, but like what I'm plotting here is that dotted line now, I didn't add any CO2 production and destruction rates. And you can see that the lines stayed at 0, meaning that when I add the CO2 SCPs, that's when I see all the oxygen being produced. I tried it with the different molecules just in case, and the different molecules render the same behavior of 5 times the oxygen production. So the main culprit that we think that produces oxygen is CO2, and it's byproducts of production and destruction. We did the same for ozone, and here we see 8 times fold of the original column Oh, I forgot the yellow lines here represents the time of the flare. So that's when the flare happens. And this is the peak of the flare when I added the SCPs to the code. We see the same thing when there's no stellar energetic particles added. The ozone stays about the same as zero. When we take out CO2, same thing happens. That stays about zero. So that means that CO2 is the one being the one affecting this production of ozone. I did the same. I took out the different types of molecules, and all of them rendered the same behavior. So CO2 was the only one who showed a zero fractional column change. Another VC plot. So in here, I just want to focus like on the top side is on the top part is just all the different column densities for the different molecules that we have in the system, how they behave throughout the flare. But on the bottom part, this is the one that I want to focus on. This is just the reaction rates for the different reactions that are important for us in this code. And you can see that the major reaction rates, for example, we have two here. We have this line, which is OH plus atomic oxygen, creating atomic hydrogen and oxygen, molecular. And this other line, which is HO2 and oxygen, creating OH and molecular oxygen. So these two are building up that oxygen that we see on the oxygen column change. So these are the ones that are creating the oxygen. And then for the ozone, before continuing, I want to show that the ozone here, it is also a high rate. And this one, it's just destroying the ozone, but this one is creating O2. So ozone is being destroyed by O2. But then remember what I show here, when I have a buildup of molecular oxygen, I'm building up the ozone. So the more ozone I destroy, the more oxygen I'm creating, but then that oxygen reverts back to ozone. So what we see is that the CO2, when we add the CO2, we get that flood, we get the oxygen from the CO2, and then the CO2 is the one being converted to molecular oxygen, and part of it converts back to ozone. So that's why we see that increase in ozone, and that increase in oxygen, and a higher increase in ozone. I also tried it with low hydrogen, but this might be wrong. I just wanted to show you just to make the case a monstro SCP FLAREMOS. That was the name of the code, because I don't know if it makes sense. It's a 200 times fold of ozone being created. So yeah, still in the works. That's all I wanted to say about this one. So in conclusion, in here, so what the conclusions are that we added the new calculations of SCPs event, and it shows an increase in oxygen and ozone. Then we see that the NOx molecules, I didn't show it, but the NOx molecules are not the ones responsible for the production of oxygen and ozone, because this tends to be something that happens in thin atmospheres, like it happened in Mars that that Nakamura was talking about. And CO2 destruction leads to production of atomic oxygen, and atomic oxygen produces molecular oxygen, and molecular oxygen produces ozone. So our future work would be to like study more that 60% CO2, low hydrogen template. We also want to create spectra for these two cases to see, can we see a difference between the atmosphere before a flare or after a flare? Another future work, I forgot to add it there, it would be to add more flare events to the atmosphere, see how that affects the overall activity of production and destruction rates for the molecules in the atmosphere. And hopefully soon we would like to publish a paper on this, so that would be really neat. Since most of this behavior, it was not what we expected. We were expecting a destruction of ozone and oxygen, but we're getting a buildup of them. So this is something that would be really good for the community to know about, and further observations and studies of M-star flares would be great for us to like understand how the flares and the SCPs can affect habitability, which is really affect the atmosphere of the planet, which relates to the habitability of the planet. And like I said, I did this in Mexico, so I just wanted to show that it was fun. It was really cool. I got to see like the Frida Kahlo Museum. I went to Teotihuacan. I saw the pyramids. I saw, I saw many things. And this is the group that I work with. Some of them were online, some of them were in person. So it was really fun to have everyone, like, it was like a cool thing that everybody speaks Spanish. I spoke Spanish, so I haven't done science like this. I don't know, like an undergrad, I was just an undergrad. So here I was just doing science in Spanish. So it was really cool to like not know words in Spanish in science, because I never said them ever in my life in Spanish. So yeah, I would like to thank. I was not gonna have a sound, so that was fun. No? Anyways, I got a mariachi. They were singing like a Puerto Rican song. I was not expecting that, so that was all. Sorry. So I would like to thank the astrobiology program for providing the funding for doing this research rotation. Also Lisa, because like I had a lot of financial issues like with the like payments, crazy things happen. So Lisa helped me like navigate those 3 months pay without pay, but then I got paid. Don't worry. And then also like Antigona, Yelena, Arturo, Marifer, Mike, which were the people in the lab of Antigona, and it was really fun. It was like a really wholesome experience, and they really helped me a lot understand this flares and SCPs and all the ATMOS code that I've never used before. So it was really great. And I would like to leave the conclusions and future work again in there. And thank you so much.
Very much, Hector.